All right, so we're going to work through the exam 2 practice. I went through it in class, but we'll work through it here. We also have the formula sheet. All right, so we're going to work through the practice exam, and I'm going to work through it on just some blank quiz 10 sheets here. And I'll talk about how we're going to go through it, and like the previous practice work through, we're gonna go pretty quickly. If you want to pause and see what's going on, just feel free to pause the video, of course. So here we go. Okay, so here we go. So problem 1, for each function, find the equation of the secant line through the points where x has the given values, and b, the equation of the tangent line. So we're going to be finding the equation of two different lines, right? So let's call this part 1, part 2 for clarity. So we're going to do part 1 and part 2. So for a, we have f of x equals x squared plus 2, right? And x goes from 3 to 5. So it's asking for the equation of the secant line through these 2 points and the equation for the tangent line at x equals 3. So if we were to plot this function just to kind of have as a frame of reference in the back of our mind, right? We're going to have, this is f of x equals x squared plus 2. Right, it's a parabola, it points up, right, and it has a y-intercept at 2, right? So if we look at the x points of 3 and 5, right, we're going to be looking at, we're going to want the secant line that goes through these 2 points, right? So we're going to want the equation of the secant line, right? The function will probably go underneath it a little bit, right? And then we're also going to want the equation to the tangent line at x equals 3 for part 2. So we're going to want the equation to this tangent line. Right, it's going to be finding the equation for these 2 lines. Of course, the secant line looks like it's going to be a little bit steeper than the tangent line. Right? Okay, so if we want to find the slope of the secant line, for the equation of the line, we can use point slope form. So we're going to have y minus y1 equals m times x minus x1, where x1, y1 is any point on the line. Any point on the line. So here, this could be the x at 3, f of 3 could be this point, or at 5, f of 5, right? And we're going to want to find the slope m, right? So the slope m is going to be y2 minus y1, so the change in y over the change in x, right? Sometimes write this as delta y over delta x, right? Change in y over change in x is going to be f of 5 minus f of 3 over 5 minus 3, right? So f of 5 here is 5 plugged into this function is 25 plus 2, which is 27. F of 3 is 9 plus 2, which is 11 over 5 minus 3. So we're going to have 16 over 2, right? And this is 8. So the slope of this line is 8. So we can now use either of these 2 points to write down the point slope form, right? So we're going to have y, we can do it with the first point, right? We're going to have y minus f of 3, right? So y minus 11 equals m, the slope, times x minus the x point, x minus 3, right? This is good enough. We can leave it here. We found the equation of that line. We could also simplify this, right, into y equals, 8x minus 24, distributing that through and adding 11 to both sides, which of course is 8x minus 13, right? So we have 8x, y equals 8x minus 13. If we use the other point, here we use the point 311, right, this point here. If we'd use the point 527 here, use this point, we would have gotten the same equation here, right? So you can use either of them, right? So that was part 1. In part 2, we want to find the equation of the tangent line at y equals 3, or x equals 3. So again, we're going to use the point slope form, and we want to know the slope. So m here is going to be, the slope of the tangent line is the derivative at that point, right? So f prime of this function, of course, f prime of x is 2x, it's just 2x, right? And so the slope at 3, f prime of 3, the slope to the tangent line at 3, is going to be 6, right? So you can write down this function, y, we can write down the equation of the line now. Y minus 11 equals slope 6 times x minus 3, because we're using the point at 311. Right? Here we couldn't use the other point, right, because this tangent line only goes through the first point. Right? And so this is the equation of our line. right? Again, we could write this as y equals 6x minus 18 plus 11, right? Distributing and adding 11 to both sides. And so this is 6x minus 7. So the line is a little bit higher, right? A little bit higher y-intercept, but also a little less steep, as we would expect. You may have just spotted the dog going by. All right, so that's part A, right? So let's go ahead and look at part B, right? So of course this is the same we found. So part B, we have f of x equals square root of x. Again, we're going to use the point slope form. So again, we're going to use this form of the line, right? And what are we going to need to find? We're going to need to find the slope, right? Again, I'll draw a picture, and you don't need to, but it's helpful to have as a reference, right? So this is the f of x equals square root of x. Looks something like this. We don't have the square root of negative values, so start x equals 0. Right, and increases, but it increases slower and slower. Okay. Right, so if we're looking between the x points, x equals 25 and x equals 36, right? So we're going to look at the tangent line between these 2 points, or the secant line. So we're going to find that secant line, and we're going to find the tangent line x equals 25. Can we see the tangent line here looks like it's a little bit steeper, right? But both of them look relatively flat. All right, so we're going to find the slope as m equals delta y over delta x equals y2 minus y1. These are just different ways of writing it, over x2 minus x1, right? And here we're going to have f of 36 minus f of 25 over 36 minus 25, right? So f of 36 function is just a square root. So we're going to have 6 minus 5, the square root of those two, over 11, right? So we're going to have 1/11 as the slope. So we can go ahead and write down the line as y. We're going to use the first point here. Y minus 5 is the y value equals the slope 1/11 x minus the x value, which is 25. Right? We're done. That's part 1. In part 2, we're going to want to find the slope of the tangent. Again, the slope of the tangent is the derivative. Slope of the derivative is the slope of the tangent line. So find f prime of x, right? And so it's 1/2 x to the minus 1/2. Right, of course it's a little easier to do this if you had originally written f of x, right, equals x to the 1/2 power, right? Then you're using the power rule, dropping that. And we can rewrite this as 1/2 square root of x, right? Maybe we can do it 2 steps, right? So this is 1/2, we can do it like this, 1/2 over 1 over x to the 1/2, right? So we just got rid of the negative power. Negative power means what's inside of that goes on the bottom of a fraction. So we got rid of the negative power, right? And then we can, of course, combine this, and 1/2 power is the square root, right? So we can kind of get there step by step. That's how we see that it's that. All right, and so we're going to want the slope at x equals 25, right? So f prime of 25 is 1/2 times the square root of 25, right? Which is 1/10. So if we write down the equation of this line, we're going to have y minus the first point, y minus 5 is the slope 1/10 x minus 25. So we're done. Right, we found the slope of those 2 lines. All right, moving on. We're going to use the product rule and or power rule, quotient rule, to find the derivative of the following functions. Right, so let's cross this out. So part A, let's see, so part A, we're going to want to take the derivative of this, right? Here we could use 2 different rules. So part A, method 1, right? We could use, you see this, we could use the method 1, we could use the product rule, right? It looks like a product rule problem, right? So we're going to say f of x equals 5x squared minus 1 times 4x plus 3, right? And so this will be our u, and this will be our v, u of x, and our v of x. And so we know from the product rule that f prime of x is going to be u prime of x, v of x, plus u of x times v prime of x, right? Each term, and one of them is differentiated into each. So we're going to have that, right? And so we know u prime, we can look at u prime and say the derivative there is 10x, right? We leave v of x the same, 4x plus 3. And u of x, plus u of x, 5x squared minus 1, and v prime is just going to be 4, right? This is good. We're done, right? We found it. That's fine as far as simplifying. I'm going to write it out a little bit more so we can see the second method is the same. 40x squared, so this is 40x squared plus 30x plus 20x squared minus 4. So if we combine, we have 40x squared plus 50x minus 4. Gotta let the dog out. And so that's also the same answer. Right, this is method 1. We use the product rule, right? We could also do this without using a product rule, which is, multiply it out. So we could do this one by writing it out as f of x equals, well, it's 5x squared minus 1 times 4x plus 3. Right, this is equal to, if we multiply this out, 20x cubed, right, minus 4x plus 15x squared minus 3, right? Now, if we want our f prime of x, we can just use the power rule, right? This is 60x squared plus 30x minus 4. Yep, we did something wrong. 60x squared plus 30x. This was an x squared, right? So when we combine this should have been 30, this should have been 60, right? This is 20x squared. So 60x squared plus 30x minus 4, right? That was method 2. Okay. So 2 ways to do that kind of problem. For part B, right, we're gonna have f of x equals x squared plus x over x minus 1. Right here, again, we can do it 2 ways. We can either use the quotient rule or the product rule. Right? If we're gonna use the quotient rule, we want it like this. If we're gonna use the product rule, we can rewrite this as x squared plus x times x minus 1 to the minus 1 power. I think it's more confusing to do this using the product rule because then you're going to have to use the chain rule on this piece. So let's stick with the quotient rule. I'll write that down. Stick with the quotient rule. Stick with the quotient rule. And so we're going to say that we're going to call this piece u of x, right? And this piece v of x. So we have f of x equals u of x over v of x. For u of x, we know is x squared plus x, and v of x is x minus 1. So we'll have by the quotient rule. So by the quotient rule, we can write this as f of x, f prime of x, right, is going to be u prime of x times v of x minus u of x times v prime of x over v of x squared. So to write this down, we have u and v, right? We're going to want u prime and v prime. So u prime of x is 2x plus 1, and v prime of x, right, is just 1. So now we can fill this in. U prime of x, 2x plus 1. V of x is x minus 1, right, minus u of x, x squared plus x, times v prime of x, which is 1, all over v of x, x minus 1 squared. And, I'm just going to go ahead and leave it there. We're done, right? That's f prime of x. Part C, right? We're going to have f of x. This is the longest one. 2x squared plus 3 times 5x plus 2 over 6x minus 7. Right? So when we take the derivative of this, I see that, of course, we could write it out and do a really long product rule, but I see doing it as a quotient rule, right? We have things divided by themselves. So you have the top and the bottom. So we'll do the quotient rule. We'll call this u of x. We'll call this v of x on the bottom. Right? And so we're going to have u of x equals 2x squared plus 3 times 5x plus 2, and v of x equal to 6x minus 7. Again, like the like the other one, like before, we're gonna need u prime and v prime. So we're gonna write u prime of x. We could use the product rule here, right? We're gonna take the derivative of the first. So we're gonna take the derivative of this, right? So we could write this, this is our a, and this is our b. So this is gonna be a prime b plus b prime a, right? So a prime, derivative of the first is 4x, right? Times b, 5x plus 2, right? Plus b prime, 5 times a, 2x squared. Again, like problem 1, we could multiply this out and use just the power rule. All right, so v prime of x, of course, is just 6. Right? So we have u prime of x and v prime of x. Cool. We can multiply this out. For u of x, 20x squared plus 8x plus 10x squared plus 15. Right? So this is 30x squared plus 8x plus 15. Cool. All right, so now we can write down f prime of x, right, is going to be u prime v plus u v prime over v squared. So u prime, right, is 30x squared plus 8x plus 15 times v, which is 6x minus 7, right, minus u, which is 2x squared plus 3 times 5x plus 2 times v prime, which is 6, right, over v squared, which is 6x minus 7 squared. All right, so we're done. We're done with it. We found the derivative. We do not need to simplify that. All right, that's problem 2. Right, and of course, this is what we got before, both in class and in the notes. All right, so problem 3, you can see the answers right away that I just wrote these down, but we can also work through it. All right, so if we go ahead and we try problem A, right? Of course, it is just, we're just going to end up using the chain rule, right? So we're going to take the inside, right? And we're going to take the outside function, we take the derivative, so drop the 3 down, subtract the 2, leave the inside the same, multiplied by the derivative of the inside, right? So we can do this piece by piece, right? So A, we have f of t equal e to the t squared plus 5t cubed, right? The cubed is really a pain in our ass. An option, if you really wanted to go crazy and you didn't want to use the chain rule, right? Maybe you had some extra time, you could write this out, right? So this is e to the t squared plus 5t times e to the t squared plus 5t, right? Times e to the t squared. I don't want to multiply it out, but if you do, you could go ahead and do that, and then you'd have smaller pieces to deal with, right? I want to do it using the chain rule, right? So I'm going to call the inside of this inside piece, I'm going to call that my my g of t, right? And then I'm going to call h of t equal to t cubed, which is the outer function, some stuff cubed, right? And so g of t, inner function, is e to the t squared plus 5t, right? And so if we wanted to write f, we could write f as h of g of t. So if we took this and we plugged it into the function that says cube everything, right? We cube it, we get f of t, right? Right. So by the chain rule, the definition of it, right, is going to tell us that. Of course, you can go and look here too, right? Chain rule, right? So if we have y is f of g, then dy is f prime of g times g prime. So derivative of the outside function, h prime, of the inside function, still the same, times the derivative of the inside function. So for us, that's going to mean the derivative of the outside function is 3t squared, right? And g prime, the derivative of this function, well, here, we can use the chain rule again, or we can just look up the rule here for exponential. E to the g of x is e to the g of x times g prime. Well, here g was just kind of any function, right? And that for us is t squared. So it's going to be e to the same function times the derivative of that function, times the derivative of t squared, and just added. So we take the derivative of that too. Okay, so we've got e to the t squared times 2t plus 5. So for f prime, right, h prime, we have 3 times all of g of t squared, so e to the t squared plus 5t squared, times the derivative of the inside, which is 2t e to the t squared plus 5, which is just this piece, right? We had g plugged in to h prime, right? So we're done, right? And of course, you could have just written this down right away. Okay, so for part B, right, we're going to have y equals natural log of a whole bunch of stuff, 5x cubed minus 2x to the 3 halves, right? so we can go ahead and work through this. If you rewrite the problem, this is a log, so you can bring powers out as constants, right? This is ln of 5x cubed minus 2x, right? This is going to be a little bit easier of a problem, but if we didn't, we can just march ahead with this one, right? So we know that the derivative of log, right, and even the derivative of log of some function is going to be, so the derivative of log, natural log, ln of some function is going to be g prime over g. So it's going to be inner function derivative over the inner function, right? So this is our inner function, right? So we know that dy dx is going to be the derivative of the inner function, right, which is 3/2. So I'm going to use the chain rule. 3/2 5x cubed minus 2x. The inside stays the same. Subtract 1 from the power, right, to the 1/2, times the derivative of the inside, which is 15x squared, right, minus 2, over the original function, the whole inside. This is 5x cubed minus 2x to the 3/2. Right, you're good, you're done. This is totally fine for me. You could simplify this one a little bit, of course, right, because this is, you have the 3/2 out front, right, and then the 1/2 and the 3/2 actually can combine, right, so you could bring this to the bottom as a negative 1/2 and then add the powers, so it's really just 15x squared minus 2, right, and when you add those powers, you're just going to have 5x cubed minus 2x, right, they're going to add to 1, because when you bring this down to the bottom, it's negative, and then you add exponents. Okay, so we're done, right, we were done before, and we're done still. If you did it this way, it's a little bit easier, right, because then we could see that dy dx, right, is going to be 3/2, constants stick around, and then it's just going to be the derivative of the inner function, 15x squared minus 2, over the inner function, 5x cubed minus 2x. Of course, this is what we got, right, so that was a little bit easier. We'll box it because we're done. Okay, that was problem 3. Moving on, problem 4. So here we have kind of the longer word problem, right? All right, so you get really warm after eating, right? According to the American Journal of Clinical Nutrition, this is a real study, the metabolic rate of a person after eats a meal tends to go up and then down, yada, yada, yada. Here's some function, right? F of t equals minus 10 to 0.29 plus 175.9 t e to the minus t over 1.3. Kind of a complicated function, right? Where this is in, kilojoules per hour. Right? Okay, so find the interval of time for which it's increasing and the time after a meal for which it's maximized. So we want to find the increasing intervals and we want to find the max, right? To find the intervals, it's of course going to be helpful for us to find the critical points, right? So we can start by finding the critical points. And to find the critical points, we're going to take f prime of t and set it equal to 0, right? So derivative, the constant goes away, right? Here I see two terms, right? This is my u of t, right? I'm going to use the product rule, u of t, and this is my v of t, right? So you're going to have the derivative of the first, which is 175.9, right, times the second, which is e to the minus t over 1.3, right? Plus, you're going to have the derivative, or you're going to have the second, 170, or the first one, 175.9t, times the derivative of the first, which is e to the minus t over 1.3. Of course, we could check our rule for a derivative of exponential things to a function, right? E to the g of x equals e to the g of x, so the top stays the same, and we take the derivative of the top piece and multiply it behind. So the derivative of minus t over 1.3 is minus 1 over 1.3, right? It's just that constant. So there we go, right? So we want to set this equal to 0 to find the critical points, right? So we're going to have 0 equals 175.9 e to the whatever plus 175.9 t times minus 1 over 1.3 e to the whatever, right? So what we can do here is we have this 175.9 e. Well, we want to set it equal to 0, right? So we want to know when this whole thing is 0. So we could divide by 175.9 e to whatever, because we know that it's never 0. So you can't divide by t, right? If you have t in both terms, because t might be 0 sometimes. So that's not allowed. But we know that e to whatever power, doesn't matter, is always going to be positive. So we can divide by that. So if we, that's one option, we can divide by 175.9 e to the minus t over 1.3. Right, and then we're going to have 0, this is divided by itself, plus t times minus 1 over 1.3. Right? Okay. So that's what happens if we divide. We could also factor it out. Factor out the e, the 175.9 e to the minus t over 1.3. It's the other way to do it, right? So then in that case, you're going to have 0 times that piece you factored out, 175.9 e minus t over 1.3, right? Times, if you pulled that out, you're going to have 1 plus the t times the minus 1 over 1.3, right? Here, again, now at this point now, you could divide by this because you know it's never 0, right? And, or you could, you know, basically you want to set this equal to 0. So if either term is 0, then you're good. You know this one isn't going to be 0, so you're really only worried about this one. You know, it's like when you're solving a quadratic, you have 0 equals x minus 9 times x minus 10, right? Because this is equal to 0, if either of them are equal to 0, it doesn't matter what the value of the other one is. So you can set these equal to 0 individually, right? In some sense, you could divide both sides by x minus 9 when x isn't 9, and then solve the problem for x not being 9, right? So for this one, you know, of course, we're not worried about this because this is not equal to 0, right? And so, again, we have the same problem. We want to solve the second part equal to 0, so we want to solve this. So 0, okay, so we can subtract 1 from both sides. Minus 1 equals t to the minus 1 over 1.3. Multiply both sides by minus 1, and then multiply both sides by 1.3. 1.3 is the critical point. Well, since we only found one critical point and we're looking for a max, good guess this is a max, right? But we want to look at, we also want to find increasing intervals. So we want to find increasing intervals and the maximum. So I think it's going to be helpful to just use the first derivative test. So we have some interval here where here t is going to be 1.3. Of course, t could go down to minus infinity, right? But I'm going to bound it at 0 for this problem. If you went to minus infinity, that's fine too. So you have the interval here, 0 to 1.3, right? And you have the interval here 1.3 to infinity. So to test whether the function is increasing or decreasing, we'll plug some values into the derivative in here and in here and see whether they're going up or down, right? Because we found the critical point here where the derivative is equal to 0, we know that it's not going to change sign. We know it's going to be always positive or always negative because it has to go through 0 to get there, to get to the other sign. So, so we're going to plug in, we can test t equals 1 here, and we can test t equals 2. We plug in t equals 1, right? We're going to be plugging into the derivative, which is this whole thing, right? I'll use the factored out part, right? Well, here's the thing. We know the exponential part is always going to be positive, right? And the 175.9, so we can divide by that because the sign doesn't matter, right? We really want to know whether this thing is positive or negative. So if we put in t equals 1, right, we're going to have something less than 1 and negative and a positive 1, right? So this is going to be positive. And if we plug in t equals 2, we're going to have something, you know, minus 2 over 1.3, something negative and bigger than 1 plus 1. So it's still going to be negative, right? So the function is going up, and then it's flat here, and then it's going down. So t equals 1.3 is a max, and the function is increasing from 0 to 1.3. Right? Done. Cool. That's problem 4. Right? Of course, that's what I found before. Okay. And so now we're doing problem 5, which came off of this one. Right, so let's fold this one over. I'm using all the extra quiz 10s because I'm not giving makeups on it. Okay, here we go. So I started doing this already, of course, So the basic idea is that, you know, you're driving a car down the road, right? Here's your little car. I've never really drawn a car before. Right? Here's your little car going down the road, right? If no other forces acted upon your car driving down the road, it would just keep going, right? If nothing slowed it down. It was going 50 miles an hour, it's going to keep going 50 miles an hour forever. This is, you know, what stays in motion, objects in motion stay in motion, right? Basic law of Newtonian physics. Is the car going to keep going at the same speed? No. Why? Because, of course, there's wind, right? So when you're going through the air, you're pushing the wind, right? So you have all the wind that you're pushing, right? And you also have the tires on the ground, and there's friction there, which is good because it lets you stop and turn. But the friction also slows you down, right? So the forces acting upon the car, so the forces, sum of the forces, right, is going to be the force of the rolling resistance plus the force of the wind. Right, and both of those are going to act the opposite way, right? You're going to have rolling resistance pushing you back and the wind pushing you back, right? So you're going to have those forces, right? Right. So the rolling resistance, you know, by the first part, you can parameterize it by it's the coefficient of rolling resistance. So it's, you know, how sticky are your tires times how much your car weighs times gravity, mass of your car, right? And the force of the wind, right, is a little more complicated, but it's 1/2 the air density, right? Times the coefficient of drag of your car times the frontal area of your car. You know, how much area is facing the wind, times the velocity of the wind squared. Right. So you have both of these terms acting upon your car. So you have the wind resistance and the rolling resistance. And it's also thought of as drag, right? And so to overcome those powers, you need power to overcome those forces, right? So the amount of power required to overcome those forces is the total number of forces times the velocity, right? This is the power required to overcome those forces, right? So, right. So if we put in values for these coefficients, right, and multiply this whole thing by v, right, we can write this as a function of v as if we put in all those values, which I'm not going to make you do, I did it for you, minus 2.68v plus 0.129 v cubed, right? I think I changed these coefficients a little bit on you guys for the one I printed out, right? So p of v, here we had, right, 0.00012v plus 0.0015 v cubed, right? And then, okay, so this is the power required to overcome the forces, right? So if you want to stay going at 50 miles an hour, you need to provide this much power for a given velocity, right? Of course, because it's cubed, the power requirement, this term, right, goes linearly, right? And the cubic term, so if you want to go faster, you're working a lot and a lot harder. This is why it's a lot harder to go 100 miles an hour than 50, right? Because the force of the wind is cubic, right? It's not exponential. It's exponential, but, well, it's actually cubic. Looks like an exponential, right? So here we go. And so the engine, right, at any given, the engine, you know, so your engine here, if you want to look at power production of your engine in like watts, right, and the fuel use, well, this is fuel usage, by power production, right? So the gas used by the car versus power production. Well, when the car is not producing any power, when it's just idling, it's using some fuel, right? And it's going to use more fuel to produce more power. So more fuel to produce more power, right? So this is a linear function, right, which we called 1.3 W plus, well, I think I changed the numbers on you again, plus 132, right? I said it's just W plus 132. Right. So for every hour, this is watts to produce this many watts for an hour. This is gas per hour, right? And this is watts produced. So to produce this much power to go a given speed, the engine is going to use this much gas per hour to produce that many watts. This is the power required to go that speed, and to produce a given power, right, the engine requires this. So we can plug P, so G of P of V is going to be the gas per hour to go a given speed, right? This function is given in terms of power production, and this is how much power you need to go a given speed. So if we plug that in, this is going to be gas per hour, right, at velocity v, right? If we plug that in, of course, we have this 0.00012 plus 0.0015 v cubed plus 132, right? And now we want to know, we want to find the optimal speed, right? So optimal speed, right, we want to write down the miles per gallon, right, which I'm going to call m, for any given velocity. How many miles per gallon do you get at any given speed, right? Well, it's going to be the miles over the gallons of gas, miles per gallon, right? So I'm going to write this as miles per hour, right? How many miles do you cover in an hour versus how many gallons do you use in an hour at that speed, right? Well, here, the miles per hour is just your velocity, right? And gallons consumed per hour at a given velocity is G of P of V, which we can just write as G of V, right? So we'll call this G of V. Right, so there we go. We have V over G of V as our miles per gallon, right? So we're going to want to maximize miles per gallon. So to maximize miles per gallon, we're going to take the derivative of the m function, right? We're going to maximize m. So we have, again, we have m equal to V over G of V, which is 0.00012, make sure I have the numbers again, right? 0012 V plus 0.0015 V cubed plus 132. Right? So this is our function for miles per gallon at a given velocity. Right? So we want to maximize this. Okay, so we want to take the derivative, right? So m prime, we're going to use the quotient rule, right? So we have derivative of the top, which is just 1, times the bottom, right? This whole thing, plus 0.0015 v cubed plus 132, right? Over, or minus the derivative of the bottom, well, the top, times the derivative of the bottom, which is going to be just this constant, plus, we're going to bring the 3 down, right? So this is 0.0045 v squared, right, over the whole bottom, squared. 0.00015 v cubed plus 132 squared, right? And so if we multiply this out, right, we're going to have, that doesn't have a v in it, right? We're going to have, and this is minus, because the quotient rule. So this term and this term are going to cancel. This term and this term are going to add up, right? We have 0.15 and minus 0.45, right? So we're going to have minus 0.0030 v cubed, right, plus 132 over this whole thing squared, right? We're setting this equal to 0, right? And we have some function squared. We want to find the critical points here, right? So we're really only concerned about where the top of this thing is 0, right? The bottom of this function will never be 0 because it's squared. So we're going to set the top equal to 0. So set the top of m prime equal to 0. So we're going to have right, cubes. Yep. So we're going to have minus 0.0030 v cubed plus 132 equal to 0. Right. I'll subtract the 132. V cubed equals minus 132. Right, and now we're going to divide by this, so we're going to have v cubed equals 132 over 0.003. Right, so we'll have to go ahead and do this part on a calculator, right? So if we turn this guy sideways, can we do cube roots on here? We can. Okay, cool. So, all right, we have 132 divided by 0.003. So this is 44,000. So v cubed equals 44,000, right? And we want to take the cube root. Done. So this is 35 miles per hour. So at 35 miles per hour for a velocity, that is going to be your maximum miles per gallon at a steady speed. So if you just cruised at 35, you'd get fantastic fuel mileage, right? Because your gas production, it's going to be better. You'd think like, okay, well, why is it quite like this? Well, if your gas, so if you were to sit still, right, you're burning gas, you're not going anywhere, right? So you're not encountering any resistance. There's no force of resistance here, but you're also not going anywhere. So if you start going a little bit, you're burning a lot of gas. Still, you're still burning hardly more gas than you weren't moving. You're not encountering much resistance. You're not going very fast, right? You go here, you're using a little bit more gas, but you're going a lot faster, right? To go and but your resistance is starting to increase. If you start to go too much faster, your resistance becomes huge, and you need to produce a ton of watts, right? So as you're producing some power, you're away from idling, right? But you're not encountering huge resistances yet. So it's you're burning a lot more gas going faster than you would be going slower. Even to cover the same amount of distance, right? Because we're covering the same v, we're covering the same miles, right? So to go 30 miles, or to go to 35 miles, you're going to get the best mileage at taking an hour to do it. Yeah. So anyway, that's our practical problem. I can guarantee you that the problem on the exam is going to be much easier than this. All right, that's all.